I'd like to thank everybody for joining us for today's live webinar hosted by Astrix and featuring Sapio Sciences. Today's topic is transforming legacy systems for the future of AI and analytics. Our speakers today are Michael Smart, who's Innovation and Client Solutions at Astrix, and Kelly Maddison. She is a Sapio Solution Engineer, obviously at Sapio Sciences. We can go to the next slide. Before we get into today's session, I want to take a moment and just introduce Astrix. If you've not been on any of our webinars, we welcome you. If you're a returning visitor to our webinars, we'd like to obviously welcome you back. In terms of who Astrix is and why we host these sessions, we are a technology and strategic services consulting firm headquartered in the United States, with offices throughout the world to support our customers. We've been doing this for about 30 years, and we bring a very unique blend of highly specialized strategic and technical services, processes, and a technology agnostic approach that has made us a leading partner in transforming the success of life sciences and science-based organizations in digital transformation. One of the things we're very proud of is the fact that over 90% of our staff hold advanced science degrees. We're very much a science-based company helping other science-based companies. And again, we've been serving the community now since 1995, which we're very proud of. So that's just a little bit about Astrix. We'll tell you how to learn more about us and Sapio at the end of the session. But with that, I'd like to introduce our speakers and then turn it over to their capable hands. So we have Michael Smart, as I mentioned, Innovation and Client Solutions here at Astrix. Michael brings over 30 years international experience. He's led digital transformation and implementation projects in the pharma, biotech, process industry sectors, brings a lot of deep technical knowledge and industry expertise to the table today. Joining him is Kelly Maddison. She's a Sapio Solutions Engineer, and she helps scientific organizations modernize their laboratory operations through informatics platforms, purpose-built for the life sciences community. So with that, I'm going to turn it over to Michael and let him start the presentation off on his side, and I will be back on to help answer questions. And again, I want to stress, as we go through the session today, feel free to ask as many questions as you want, and we'll take a few moments at the end to help field those. Michael, it's in your hands.
Yep. Hello all. So today, Kelly and I are going to talk about modernization, and specifically the challenges of unstructured and legacy data, how to build a foundation that helps deal with that and position things to be able to leverage AI and analytics to best effect. Kelly's going to show us within the Sapio platform some of the exciting things that can be done if we have the right foundations in place. So we hope that coming out of this, you'll have a better appreciation for some of the key blockers to modernization, some of the foundational capabilities that are key to enable our lab of the future aspirations, and what an AI native destination can look like. So we have broken today's webinar into 3 parts, or acts as we've called them. In Act 1, we will talk about the typical current situation that many labs find themselves in, and some of the main reasons that lab modernization fails, with a particular focus on data. In Act 2, we will discuss some of the foundational capabilities that need to be established in the systems environment and with data in order to be positioned to be able to use the power of AI to best effect. The final act, Act 3, we will show you, using Sapio's informatics platform, some of the ways that AI tools can help accelerate the scientific process once we have these foundations established. So we appreciate there's a big range in the maturity levels of labs, with some organizations just getting started on their digital transformation, while others have been on that road for some time. Having said that, on the left is what a typical technical landscape looks like in many of the organizations that we work with. At the lab systems level, there are usually, multiple systems in play to capture different types of information. The data are siloed across those multiple systems. Each system usually manages its own master data and controlled vocabulary terminologies. So definitions of meaning are inconsistent. So even though the data are digitized, a lot of it is still in semi-structured or unstructured form, such as documents. Additionally, the individual systems usually don't talk to each other very well, so coordinating workflows and data exchange across systems is difficult, or such workflows or data flows are often enabled through point-to-point integrations. And we then typically see organizations bringing the data from those lab systems into the data layer, where we use integration tools to harmonize it and join it together so that we can apply reporting and analytics. This is usually a complicated and time-consuming effort. The lack of shared data meaning, metadata, and context makes integration and reuse difficult. Organizations often repeatedly spend time reconciling those definitions, preparing data, rebuilding similar pipelines across different teams. As organizations push further into advanced analytics and AI, these foundational gaps become more visible and impactful. The unstructured and semi-structured data typically presents us with some specific challenges. Much of our data, and certainly legacy data, are often in this form. So take ELN data, for instance. Many of those systems are still what we call paper on glass, i.e. they just digitize what we used to do in paper, and they provide little in the way of structuring. So looking at the example on the left, best case, we may have some structured business metadata like project or target, and some basic structuring into sections, but the majority is often free-form text that does not use any standardized terminology. Just looking at that example, the impact is clear. How can we answer questions like, what is this experiment about? What are the key concepts here? How should we identify the main concept? Is that ST2, or are there other identifiers or synonyms that are important? Is it related to other key concepts that should be highlighted? And what analytical methods were used? Can I find other experiments using the same analytical method? All these types of questions are difficult to answer if we don't have standardized terminology and semantic linkage between concepts. If we as humans are struggling, then we can't expect machines to do much better. Even though our AI LLM models are good, and they don't need a whole lot of structured information to work, but they do a whole lot better if they have an understanding of our scientific and business terminology and the linkages between those concepts. So other compounding problems that impede lab modernization include the lack of orchestration across those fragmented systems. We ultimately want AI to facilitate workflow and data flow and be able to take action, not just analyze and suggest things. So to do this, we need systems and capabilities that are going to allow that. Data are still largely optimized for those individual applications, not for integration and reuse. So data management capabilities and associated data governance really need to take center stage to implement the right data constructs like ontologies and ensure that those are applied. Resistance to change is another key barrier. This includes the use of new tools and the application of good data management concepts. AI and intelligent workflow can help guide, suggest, and facilitate the use of new tools and generally lower barriers to adoption. So that is a key area that we will talk a little bit about. So moving into Act 2, how do we move from siloed to harmonized? Two key foundational pieces within our technical architecture that we see as fundamental in helping to move us from our fragmented data state to a more interconnected, context-rich, and reusable data state are orchestration services, highlighted there in orange, and ontology-aligned reference data, highlighted there in so in green. So the former allows us to connect our systems together in a programmatic and non-point-to-point way and effect automated workflow and data flow, and the latter provides shared business meaning and enables data interoperability and facilitates AI and ML. So what is ontology-aligned reference data? In order for us to have a shared understanding of the key business objects in a specific domain and how they relate to one another, we need to develop simple data models that represent those business concepts and semantic relationships. So those models can typically be represented in machine readable form as ontologies. Behind each of the classes are real world instances that we label, i.e. we have multiple process stages that we run, and those process stages have names like vial, thaw, and expansion. This is the terminology that we use to describe things. If we don't use the same terminology and understand what concepts that terminology is used for, it becomes very difficult to compare information. There are many ontologies and terminologies that are publicly available, as well as some commercially developed solutions. These often provide a starting point for things, but there are always organizational customizations or additions to these. So the ontologies and terminologies that we use to describe our data domain are what we call our reference data. Again, consistent reference data helps us humans and machines understand that the business terminology used and how things relate to each other. Reference data are an important part of data management. Not the only thing. There are other data management concepts such as master data and metadata management, which are important, but we're not going to focus on those here today. Importantly, the reference data is not static. It's constantly evolving as new processes and scientific methods are developed and revised. So why does ontology-aligned reference data matter? We're revisiting our semi-structured sort of ELN data example from before. Here is a search example that illustrates the importance of ontology and aligned terminologies. If I were to perform a simple text search for IL1, RL1, this experiment wouldn't show up because that isn't mentioned anywhere. However, if I have an ontology-aligned reference data in place, I would know that ST2 is an expression protein of IL1, RL1. Therefore, I can infer this experiment is also about IL1, RL1. I can also reconcile the different synonyms for ST2, SST-2, etc., and understand that they refer to the same thing. So reference data often looks deceptively simple, but in practice, it can become one of the biggest barriers to interoperability. So how do we define reference data in practice? Typically we start out establishing that data domain model. This can be relatively simple to start with, or it can leverage those existing ontology models. We then identify our key business use cases within the domain. Then follows an iterative process of use case at a time. We go through, we analyze what the data outputs and inputs are for those particular use cases. We identify the terminologies being used, and then we compare to the domain model, and align on common terms, add new terms, and decide if we need to update the model itself, etc. So it is a time-consuming process, it takes a lot of SME time, and it also needs to be maintained. Again, not just a static process. The AI tools can certainly be employed here to reduce the effort and duration of constructing and maintaining the reference data. But once we have established that reference data, this terminology then needs to be applied at various levels, including source systems, which is often hard to do because those systems don't want to consume external reference sources. We also have a lot of people bringing things in from different sources, and so difficult to do that often at source systems. We need to apply our reference data at the data layer. That is typically easier and normally where we see things being implemented, but still involves employing integration, normalization, data pipelines, and then using our reference data ontology to retroactively analyze tag reference data that we have with concepts and synonym linkages. So establishing ontology-aligned reference data and orchestration workflow and data flow capabilities are foundational for AI and automation. Without semantic data structure and orchestration, really the use of AI in our lab is really just a chatbot. With it, it starts to become a co-scientist. So what does an AI native destination actually look like? And at this point, I'm going to hand off to Kelly to show us some of the exciting things in the Sapio's platform.
Thank you, Michael. Just to double check that you can hear me before I start.
Yep.
Yeah, perfect. Great. Thank you so much. I think it's a really common theme, what Michael has been talking about, and we need to acknowledge that the foundation is critical in order to have a successful software implementation. So that's what I'm going to talk about today. And I will be referencing back a lot to what Michael has been talking about. And hopefully it will become clear why it's so important before we go ahead and implement a scientific platform where we use AI and utilize AI. Okay, so we've spent the first 2 acts talking about the problem and the foundation. So now let's talk about the destination, so where the data is actually going to end up. And what does that look like when the platform is built on the use of the foundation from day one? So when we have all of our foundation aligned, how important that is to then utilize a software platform. So at Sapio, we've built a single scalable informatics platform that spans different functionality across LIMS and ELN. It's designed to serve a very different lab environment, so it can span R&D, clinical diagnostics, and GMP drug manufacturing. But what I really want to talk about today and draw your attention to is the architecture underneath all of those capabilities. So what you can see at the bottom of this screen is a lot of functionalities around configurable data model, no-code rules engine, real-time collaboration so you can talk with scientists within the platform itself, advanced analytics, permission-based access. All of these functionalities aren't add-ons, they're built within the platform. So at any area of the platform, whether you're in the ELN or the LIMS, you can utilize all of these functionalities. And the reason that this matters so much, and it's very important, and it connects directly with what Michael was talking about today, is that a platform like this can actually use ontology-aligned, harmonized data within these functionalities, and it can reason over specific things that we're asking scientifically day to day. It can surface it within context of the science that you're performing, but without that underlying foundation that Michael was talking about, ultimately we just have a platform that you can't reutilize your data effectively. So what I'm aiming to do is bridge the gap between Act 2 and Act 3, which is what we're in now. And so the foundation that Michael has described, I'm going to show you the value that can be drawn from a scientific platform that's built on that foundation. Okay, so if we think back about the different generations of ELNs, so the first generation ultimately was pretty much a paper on glass scenario. So it was somewhere where you could record or capture records, tick some compliance boxes, so you're not using paper anymore. It is a lot more compliant in the sense of everything is being tracked in one location. It was a step forward, obviously, to using paper lab notebooks, but it's still a very fundamentally passive process. So the second generation was pretty much the similar concept, but we had slightly better functionality and collaboration features, workflow automation. So everything was like a little bit faster, a little bit easier to record, but still pretty much a very passive process. So the scientists still had to know what they were looking for, how to structure their experiments, and how to interpret the results. So ultimately, still, even within the second generation, the ELN is just a keeper of all of your records. So what we're moving towards now is the third generation. So this is what we call AI assisted lab notebooks. AILN is what we're calling it today within Sapio. And this is a fundamental inversion. So instead of the scientist learning and understanding the ELN actually understands the scientist and what they're trying to do day to day. So instead of the scientist having to extract information to design and analyze their experiments, the ELN AI system is becoming an active advisor. So it's advising on experimental design. It can help the scientist create protocols. It can assist in the execution and the analysis of that data. So this is where we're seeing the massive shift in terms of going from the first and second generation of ELNs, which is very passive, to the third generation, which is very active. However, this is only going to be possible if the underlying data is structured. So it's coherent, it's machine readable, and that's exactly what Michael was talking about in Acts 1 and Acts 2. So a few examples I have to walk through now. So one of the most common frustrations that we hear from scientists in the lab is, I know my data exists, I just can't find it anywhere. So traditionally in the first or second generations of ELNs, it's still kind of a fragmented, siloed system. So you're potentially still using Excel files, Word documents, PDFs with your data on it. And you can't necessarily collate your data in a structured format to be able to reuse it and derive value out of it very easily and quickly. So here's an example of how we can start utilizing Elaine with our structured data. So this is a real scientific search. So I want to find all of the samples I created last year with a Sykes calculator concentration greater than 400. So it's a natural language prompt. There's no query builder, no SQL, no drop-down menus. It's just a simple prompt that a scientist has asked the platform or the AI agent within the platform. So what Elaine is doing is it's interpreting the intent of that query. So it maps it to the underlying data model that's within the platform. So it knows exactly what to look for, exactly what data to pull out. So instrument data, sample records, calculated values, and it will populate all of that data into a structured format where the scientists can reuse it, make decisions a lot faster because they can see it in a structured, clear format instead of getting values from Excel files and putting them into another Excel file and so on. So this is the real value that we're seeing with search and prompts, where the foundational data is already structured so that the AI agent knows exactly what to pull and then format it in a way that we can reuse it. So here is the exact same query that's broken down into the advanced search. So that's something that our AI does automatically for us. So this is good for two reasons. One, because we can sanity check that that prompt is accurate and correct, and two, we can learn how to do these advanced searches if we want to do it that way in the future. Here we have the opportunity to add additional terms to our query, and then really just break down that data set even more if we need to. So ultimately what we have here and what we're seeing is the same natural language interface, but it's now joining data across multiple dimensions. So we've got the sample provenance, we've got the instrument type, and we've got the analytical result. So in a traditional system, this might take a data analyst, well, probably days, and most of the time in my experience, especially when I was working in the lab, I'd probably just give up because it just is too time consuming to perform manual extractions of data and populate it into one single location. So here, doing it this way, it just means any scientist can do it quickly and easily, and again, derive value from that data, make decisions on the next steps, and so on and so forth. So the reason this works so well and I want to be very explicit about this, is because the underlying data is well structured and semantically tagged. So ontology aligned reference data, as Michael described earlier, means Elaine can understand what the term SciAx refers to, or what the term the calculated concentration actually maps to, and how those concepts relate to each other. So without that foundation, it's ultimately just a keyword search where you're not gaining much value out of it. But if you have that ontology aligned data within the platform already, you can just utilize Elaine or the AI most effectively to see exactly what you're looking for with your data sets. Okay, that's just the prompt again. And here again, we can just see that data that's populated after the prompt has been executed within the platform. Okay, so the next example, and a very common one, is SOP to experiment. So it's another effective tool that we can use with our AI to help save time with the scientists having to manually build experimental templates within a digital platform. So imagine you have an SOP and it's just sitting in a document management system or a SharePoint folder, or maybe it's been potentially emailed to you as a PDF or so on. And every time you need to run an experiment, someone somewhere has to ultimately transcribe the steps from that SOP. So for example, setting up the reagent step, configuring the instrument parameter step within a template that then can be followed by analysts within the lab. Clearly, this is a very time-consuming process. It can result in error-prone steps, and frankly, it's a waste of time for the scientists to be performing this, because ultimately they just want to be doing the manual work in the lab, generating that data. So the functionality that we have within Sapio with the use of AI is that we can take the SOP document and automatically generate, or allow it to automatically generate, a fully structured experiment from that. So in this case, you can see here, you just upload a specific protocol, so any file format that you might have. And on the left-hand side, you use the chat box functionality that's available within your ELN, within the Sapio platform, put in your prompt, and then it will start building out a template for you automatically without you actually having to do any manual steps. So if I just click through this and show some examples, so what we have is the prompt being executed, and then some various tabs at the top of the screen, which is your procedure details, your plating and sample preparation, your run, and then your results and analysis. So if I just click through these and show you how it's been built out automatically. So it's built out our samples table, it's built out the material step, so it's detected which material types we should be using as part of that specific SOP. It's automatically added a plating step for us and populated the samples in specific locations if that was also specified in the SOP. It will have our instrument run parameters automatically populated as well in a structured table, so we can utilize those steps. And then after, we can start using AI to then do the results and analysis. So what you're seeing here isn't a template specifically being filled out, it's just being created. And Elaine is actually interpreting the meaning of the SOP and mapping it into the platform's data model. That's only possible because of two things. So a capable AI layer and a data model that's expressive enough to capture scientific context. So this is hours of manual work for the scientists compressed into seconds. And more importantly, it removes a significant source of transcription error from the workflow itself. So again, the analysts are just having to add in their specific values for the specific steps and not actually manually transcribing long steps for the setup of that template. Okay, this is just another example of some data analysis and visualization, so our charting capabilities that are within our platform. Okay, so if we think about finding the data, which is great and it saves us a lot of time, but it still is only half of the battle that's been solved. So the other half is the interpretation. And that's where a lot of scientists' time gets consumed with interpreting all of their data sets. What we can now do again with Elaine is surface search results, so it can assist with the analysis and interpretation of our data sets. So rather than exporting to Excel files and manually reviewing, scientists can actually ask follow-up questions from the data sets that's been generated, ask questions around what are the outliers, what does this cohort compare to in previous runs, are there any samples that fall outside specific specifications, and so on. So here again is just another example. So what we have is a data set that's, again, similarly to the previous example where we had the search query builder. It's an advanced search where we've prompted the system, it's generated our data set for us. And you can see here we have the chat with Elaine functionality available on this screen. So we can use that and then prompt some further follow-up questions to analyze our data sets. So here this example is comparing concentration data from the same sample that has been run on multiple instruments. Is there any discrepancy of more than 5% between the concentrations reported by instrument TS5, TS1, or TS2? So this is quite a complex query if you are searching through a lot of manual Excel files and so on. But here again, we can utilize the AI to find this data or prompt this data quickly to then again, make decisions from our data sets faster. So after that prompt has been initiated, we receive a report back, which gives us all of that information. So if there were any discrepancies, which we can then use to compare against each other. And then we can further use that data set or that report to generate more charting and visualization tools to really understand what that data set is actually telling us. So this is Elaine becoming an active analytical partner. So it's not just a system of record, but it's a system of insights. The quality of those insights is going to be directly tied to the quality of the underlying data. So how structured is the data? How harmonized is the data? Are your ontologies aligned? Which would then mean that the AI can draw meaningful comparisons and flag meaningful anomalies. Okay, so another example we have here. So I want to highlight something on this slide. So not all AI actions have to be prompted. So this is a subtle but important distinction. So most AI tools today are reactive. So you ultimately ask a question and it will answer the question. But what we're moving forward now with Elaine and Sapio is a proactive AI. So where the system will recognize the context and take action from that. So here we have a study design document, which can come in from, perhaps like a project management system or a client that you can import into Sapio. Sapio will read that document and understand the study parameters and automatically generate the corresponding study structure within the Sapio platform. So there's no manual setup required, no interpretation required from the scientists. Ultimately, all they need to do is import the document. Sapio knows how to read and interpret that document, and it will populate a structured study design within the platform that we can then use as we work through the manual steps of that study in the lab. So this is an example of what it would look like once it's been imported. So once it's read the document, it will populate all of these tabs for us with specific information. And this is exactly what we're meaning now by the agentic AI. So it's not just answering questions, it's actively building and helping you complete specific workflows. So think about what this means at scale. So if every study that comes in is triggered with an automatic setup, so these templates, these workflows are being built automatically, it just takes away that tedious, time-consuming process from the scientists, and then they can then spend their time doing the actual science and not configuring the platform. Okay, so another example here. So this slide shows Elaine working within with real experimental data. So in this case, we have a binding assay measuring activity across dopamine, serotonin, and other transporters. Traditionally, a scientist would export this data, potentially run it through a statistical package, or manually review it in a spreadsheet. Again, very time consuming. They'd write up their interpretation and then draw conclusions from that interpretation, which could take a very long time to do so. So Elaine can now assist with all of those steps directly within the ELN. So if I just click through some examples here, we've prompted Elaine to analyze the data in the assay results. So again, it's going to build out some steps for us automatically. So what you're seeing here is Elaine that's automatically populated this information. So it's got the overview, it's got the top compounds that have been listed, it's got the potency binding and so on and so forth. It then builds out tables for us. So we've got the top 25 DAT selectivity in that table. Again, we've got all of that information populated as well, so no transcription required for these steps. Again, we can chart this data. So as soon as the data is in a structured format, aka one of those tables that you've just seen, we can use the charting and visualization tools to quickly create these charts, either ad hoc or automatically within these templates. So ultimately, if I just go back one step, so it can identify information such as, in this case, which compounds show the most potent or selective binding profiles. It can flag the anomalies. It can compare the results set to historical data, so if you have previous runs. And it can do all of this in a response to a plain language question from the scientist. So analyze my results, which was the example in this case. So what I want to emphasize particularly here is that this isn't a generic AI tool reading a CSV file. Elaine understands the scientific context of the data that is being input into the system. It understands from that data what the assay type was. So in this case, the biological targets, the units, the significance of all of those values, because that context is encoded within the platform's data model. And that this is what we're talking about with, it's not just AI, it's scientifically aware AI, which actually helps us in the scientific work that we're doing day to day. Okay, so what you've seen across those particular examples or demos is a consistent theme. So Elaine reduces friction at every stage of the scientific workflow, from finding data to setting up experiments, to analyzing your results, to generating studies from documents and so on. So the platform is actively working alongside the scientists, not waiting to be told exactly what needs to be done. And critically, every single one of these capabilities depends on the foundational work that Michael was talking about in Act 1 and Act 2. But if we're honest about limitations and LLMs alone, even a powerful one, it can ultimately only get you so far. So it can understand language, it can generate text, it can reason about some specific problems, but it can't run a blast search, it can't perform a retrosynthesis, it can't inherently know which statistical test is appropriate for your binding assay. So that's one of the things that we are moving forward to today. And it's not just an LLM alone, it's an AI, agentic AI that knows exactly what the scientist is trying to do. One of the biggest misconceptions here about AI in the lab is that a powerful language model by itself, a scientific assistant, is two different things ultimately. So it's not one AI tool that's working to help the scientists day to day. So we're using other systems to help the scientific aware platform understand exactly what it needs to do. So if we move beyond an AI that can tell us or tell you how to use Sapio to one that actually thinks alongside you within an experiment, we have to close that gap. So we have to build Elaine to do exactly that ultimately. So Elaine acts as a bridge between the language reasoning of models like Claude and ChatGPT running on Amazon Bedrock, and then the scientific computing layer inside the Sapio platform. So it gives the model three critical things: access to the right analytical algorithms, contextual awareness to know which algorithm a given question needs to be called, and the ability to pull real scientific objects in, so compounds, sequences, assay results directly from an experiment, and it will reason over that information. And that's what transforms a simple chatbot into a co-scientific chatbot ultimately that we're using now within Sapio. So what does that actually look like today? So as of our latest release, which is 25.9, Elaine ships with a growing library of scientific agents across three core domains. So in informatics, researchers can run retrosynthesis to work backwards from a target molecule, check viability, optimize reaction conditions, and so on. On the bioinformatics side, so we've got a lane that can run blast searches, perform multi-sequence alignments, and handle codon optimization for protein expressions. Oh, sorry, just went. So these capabilities would typically require a specialized tool and significant setup time, but this is something that we already have built within the platform. For the structure-based design specifically, the platform connects to PDB for structure lookup, support molecule generation, and can run docking simulations. So none of this is built from scratch. We've partnered with the best tools, so Ascos from MIT, DeepChem, NVIDIA for compute, and so on and so forth, and made those tools all accessible as intelligent agents that scientists can evoke conversationally within the platform. So this is the compounding value here. So it's not just any one of these capabilities, it's all of them working together in context to form that co-scientist functionality with our AI. So on this slide, this captures the fundamental shift that we've been walking through today. So on the vertical axis, we've got the scientific support, so how much the system is actively helping the scientists. And on the horizontal axis, we've got learning and usage barrier, so how much the scientist has to invest to get value out of the system. So traditional ELN systems of record sit at the bottom, so the bottom right. So high barrier to learn, high burden to use, low active support, and scientists spend their time learning the system rather than actually doing the science, sorry. So Elaine flips this entirely. So zero learning barrier, scientists interact in natural language, the way that they already think and communicate, day to day, and high scientific support. So the platform actively advises, it creates and executes and analyzes alongside them, so saving them a lot of time. So this isn't just an incremental improvement, it's a generational shift from how we're using our AI within laboratory informatics and how we can actually do science day to day. So this is the slide that is going to tie everything together that we've been talking about today. And I think it's probably the most important one of the day. So we've told a 3-act story. So step 1, naming the real blockers. So it's not the technology, it's unstructured data, the missing semantics and the fragmented systems, the legacy trap that Michael was talking about. And then in step 2, we were talking about ontologies as the substrate. So harmonized vocabularies applied at the integration layer that can give data shared meaning and machine readability. And then we moved on to step 3. So where we can actually utilize our foundational setup to work in a digital platform that then again uses AI. So Sapio showed the destination, so the AI native, agentic, scientifically aware platform, one that is built to use the foundation and not just work. So the takeaway today, I would say, is you cannot AI your way out of legacy data debt. So we see it again and again. So organizations invest massive amounts of money in AI tooling to get disappointing results ultimately, because they do not have that foundation that's already preset. But the second half of that sentence is equally important. So the destination platform determines whether AI is a daily tool or just a demo system. So foundational plus destination, that's the joint thesis. And that's what Astrix and Sapio are bringing together. So I really hope that made sense. And it's clear to you about, the importance of having that foundation before implementing an AI system or an AI focused system. So with that, I think we have come to the end.
Yes, thank you so much. Great presentation, Michael and Kelly. Super informative. And thank you for everybody for hanging with us through that. I hope you found it very informative and helpful. A couple things here before we get into the questions. Obviously, if there's any specific questions you have, either of Astrix or Sapio, the best thing to do is to jump out to the website there on both. So we'll leave that up for a second. And we obviously encourage you to do that. If you have any questions now, great time to start asking them. I do have a couple on the floor I'll get to in just a second, but if you have something you haven't asked yet, just go to the question function on GoToWebinar and type that in. We will send a recording of this out at some point, probably early next week. It'll have a copy of the recording, a link to the YouTube channel for Astrix with all of our sessions on it. And obviously, if you've asked a question and we don't get a chance to answer it, we'll hit you up directly. So with that, I'm going to go ahead and stop the recording.